Today we're going to learn about the asymptotic equipartition property, AEP. It's a fancy name but relies on a few familiar concepts, so we're going to make the overview as clear as possible using cats. The asymptotic equipartition property is an important theorem in information theory. It relates to sequences of random events, like a sequence of coin flips, or a cat which spends each day either meowing or sleeping. When you have a really long sequence of the random events, there are a lot of possible outcomes. But AEP says that among those many possible sequences, only a small subset will occur in practice, although each of those typical sequences is equally likely. This theorem is used in compression, where it allows us to come up with efficient codes for sending bits across a channel. AEP is also used in error correction for reliable data communication, where we can detect if a faulty device accidentally flipped a bit and recover what the message was intended to be. On our channel, we already have a video that gives a short overview of AEP with a cat named Ella. In this video, we will continue with our friends Ashley, Ella, and Bill, but we delve deeper into the mathematical concepts behind AEP and present a proof. It'll be helpful if you already have a basic understanding of probability, so feel free to pause, watch one of the linked videos, and come back to ours. Alright, so quick recap of our characters. We have two siblings, Ashley and Bill. They have a super cute cat named Ella. Now they're stuck at home because there's a global pandemic happening. And Ella meows all the time. Although occasionally she has a really sleepy, quiet day and doesn't meow at all. One day, Ashley and Bill decide to start keeping track of the days when Ella meows, M, or sleeps, S. Call this random variable xi for day I. They decide it's reasonable to assume the xi are independently and identically distributed. This means whether Ella meows or sleeps today is not affected by what she did yesterday or any time in the past. Whatever tells her deep down inside how to behave doesn't change from day to day. They notice that about 10% of the time, Ella spends the whole day sleeping. More often, she's meowing away. We can write this mathematically as the probability that xi equals m is 0.9, and the probability that xi equals s is 0.1. Now it's one thing to compute the probability of Ella meowing or sleeping on a single day, but what about if we want to figure out how likely a sequence of days is? This is called computing the joint probability. Because the xi are independent, we can split the probability into a product of probabilities for each random variable. The sequence of 10 days in a row where Ella meows every day has the probability 0.9 to the 10, which is about 34.9%. And the sequence where she has one sleepy day but 9 noisy days only has likelihood 0.9 to the 9 times 0.1 to the 1, or 3.9%. This is kind of weird if you think about it, because we expect about 1 out of every 10 days to be sleepy and the remaining to have meows. In fact, AEP will tell us this does happen, that most of Ella's sequences will have about 10% sleepy days and 90% noisy days, but only as the sequences get very, very long. To start thinking about sequences that get longer and longer over time, let's imagine many parallel universes in which Ashley, Bill, and Ella run this experiment. Each universe is identical, but we get different sequences since Ella's cat soul telling her whether to meow or be quiet is a random variable that doesn't depend on anything else. Now, the only reason we're using parallel universes is to make it easier to think about independent observations. Don't worry, we're not going to talk about physics. Ashley and Bill wonder which sequences will occur, especially as time goes on. There's only one outcome with 30 meow days in a row, but many outcomes that have at least one silent day. Even if the sequence of 30 meow days has the highest probability out of all length 30 sequences, it is just a tiny sliver. The sliver shrinks quickly because the number of all possible length n sequences grows exponentially. Now Bill invents a game for Ashley. He gives her a pile of coins, and she has to distribute coins across sequences to bet which outcomes will occur in the Multiverse, where we run the experiment with Ella for 30 days. Ashley doesn't have enough coins to bet on all sequences, so she has to strategize wisely. If she picks a sequence that doesn't happen in any universe, she has to pay, but if an outcome is on one she chose, she wins the coins that she bet. Now, Ashley could come up with all sorts of strategies. She could risk it all in one sequence or try to distribute over a lot of different sequences. Ashley is trying to pick the best strategy when she realizes this is a perfect application for AEP. The asymptotic equipartition property involves looking at all possible sequences of meowing or sleeping and tells us that only a small fraction of them will occur in practice. This special subset is called the typical set. First, we know that Ella being silent every day is not in the typical set. That cat really likes to talk. But we can see an example of a typical sequence too. Maybe Ella has a few noisy days, then a quiet one, then back to meowing. Now we mentioned this earlier, so here's a pop quiz. Is a sequence of meowing for a whole bunch of days in the typical set? Although the sequence might have high probability, it is not typical. It doesn't represent most outcomes across universes, since Ella has noisier and quieter days and shows a non-constant distribution. Counterintuitively, the most likely sequence is often not in the typical set. It becomes more and more atypical the longer Ella's streak of meowing goes unbroken. So how do we mathematically define the typical set, and how can Ashley figure out which sequences are in it? Let's go back to our parallel universes. For any possible sequence, we can assign a likelihood of it happening. By assuming independence of Ella's behavior across days, the probability of a particular sequence occurring is simply the product of probabilities for individual days. Now we're ready for the formal statement of AEP. The sequences we're referring to are the outcomes x1, x2, all the way through xn. Remember, each xi is either m or s depending on how Ella acted on day I. We use the notation a to the n to mean the typical set of sequences of length n. The asymptotic equipartition property says that as n goes to infinity, the probability of the sequence x1 through xn being in the typical set has a limit of 1. We're going to keep talking about this definition, but here is just a first statement. Now, the asymptotic part. This means the size of the typical set will shrink exponentially as n goes to infinity. Despite this, AEP says that the probability of a sequence being in the typical set as the sequence gets longer and longer approaches 1. Next, equipartition. The other part of the statement of AEP is that each typical sequence is equiprobable, equally likely. To think about a concrete example, if we run the experiment for just a few days, we could really get any kind of sequence. Maybe Ella sleeps for 3 days in a row. But if we run the experiment for longer, the sequences that happen are probably going to be typical ones, with about 10% sleepy days and 90% noisy days. We will go over the proof of AEP later, but it relies on the idea that things tend towards an average. Ella might have 11 meow days in a row, which would be unusual if we look at only that part of the sequence. But as we look at the sequence as a whole, there will be sleepy days too, and the sequence will be more typical. Now, to win in Bill's game, Ashley needs to figure out which sequences are in the typical set. Her big trick is that there is a probability which typical sequences cluster around. She computes the probability of every sequence and creates a histogram. For each possible probability between 0 and 1, a bar indicates the number of sequences with that probability of occurring. Ashley observes 3 kinds of sequences. Those that have a relatively high probability, and there aren't a lot of those, the bars are so tiny. Ones that almost never occur, and almost all sequences are of this type. And a group in between, a small set of sequences that are equiprobable or equally likely. In our example, there are over 1 billion sequences of length 30, but when Ashley counts how many sequences are in that middle cluster, there are only about 17,000. This is a really tiny fraction of the total, but they each have probability approximately 1 over 17,000, so the subset holds almost all the probability. Ashley has figured out the probability that sequences in the typical set will have. In essence, AEP filters out a small number of highly likely sequences and a lot of highly unlikely sequences to leave us with the typical set consisting of a few sequences that are all moderately likely. So, to recap Ashley's winning strategy, first she figures out the target probability that sequences in the typical set have, then she lists all length n sequences, and selects the ones with the target probability of occurring. She places her coins evenly across these sequences. By AEP, the sequences that occur in the multiverse are almost certainly from the typical set. Ashley basically can't lose. So we've talked about what AEP means and how it can be used in our example, but what is the proof of the theorem? Here's the formal statement of AEP we gave before. Now that we've talked about how typical sequences all have the same probability of occurring, let's write the theorem in a different way. So we can also say that the probability of a very long sequence is approximately the typical probability. More rigorously, this is convergence in probability. And here's the final version we will work with in our proof. There is a constant p-typical around which the probability of the sequence x concentrates. Let's begin with how we calculate the typical probability p-typical. A typical 30-day period contains 3 silent days and the rest have meows. Since each day is independent, we calculate the joint probability as 0.9 to the 27 times 0.1 to the 3 and get back 0.000006. We can also calculate the probability of a sequence with just one silent day. It's actually a much higher probability than what we said was the typical probability, 0.005 versus 0.00006. One important concept to keep in mind before we go into the proof is that the probability of random sequences is also a random variable. We can consider these probabilities as a new random variable p. Another way to think about this is that a function of a random variable is also a random variable. So, taking the probability is a function mapping from the sequence x to a number. We can also write down the distribution of this new random variable p. For example, what's the probability of p being 0.00006? That will be the probability of having sequences of 27 m's and 3 s's. There are 30 to choose 27 such sequences, and the probability of each sequence is 0.9 to the 27 times 0.1 to the 3. Now, the AEP states that if we draw the distribution of this new random variable p, the distribution of p concentrates around p typical as n goes to infinity. Now let's prove that p is almost always p typical. We will use the law of large numbers to prove this. The law of large numbers states the following. Let y1 through yn be n independently and identically distributed observations of the random variable y. Then the average of these n observations will be very close to the expected value of y, with high probability. This says that if you have a really large number of IID observations, you cannot predict the outcome of each observation, but you can predict the mean of the observations with very high confidence. Let's see how we can apply the law of large numbers in our problem. Remember that since x1 through xn are all independent, the probability of the sequence x is simply the product of probability of each observation. To use the law of large numbers, we will need to deal with sums. So we transform the product of probabilities into a sum by taking the logarithm. If we take the log base 2 on both sides, the product becomes a sum. Now proving that p concentrates around p typical becomes proving that log base 2 of p concentrates around log base 2 of p typical. Now let's denote log base 2 of the probability of x1 as y1, log base 2 for the probability of x2 as y2, and so on. After dividing both sides by n, we get this equation, which looks very similar to the one inside the probability in the law of large numbers. In fact, if we let p typical be 2 to the n times the expected value of y, this equation becomes exactly the one in the law of large numbers. Hence, this approximate equality holds with probability almost 1. This completes the proof. One last note. During our proof, we found that the typical probability involves the expected value of y. In fact, this quantity is more often called entropy, denoted h. We encourage you to learn more about entropy and AEP from your favorite information theory books or videos.